My name is Joseph Ma. I'm a PhD graduate from Singapore Geophysics project. Today I'm happy here to share with you our most recent research on characterizing single fractures from their flow elastic properties. So let's start off by giving an introduction on why fractures are important in terms of elasticity and flow capabilities. So any separation in geological formation can be called rock fractures, and if in a piece of rock we're introducing a fracture in it, this continuity in rock body is actually introducing a mechanical weakness to host rock. So the significance of this is that the rock and the fracture interface, they are more prone to subsequent deformations and relative movement. So essentially the rock body becomes more weak. And typical rock fracture spacings in field environment ranges from tens of centimeters to tens of meters. So we can be seeing fractures of various length scale in actual conditions. For example, earthquake faults can span between hundreds of meters to kilometers, and typical natural fractures in aquifer environment could be centimeters to meters scale, and not to mention fractures can also exist in man-made structures in concrete. And in engineering environment, when we deal with subsurface, the significance of fracture is also pretty apparent in the flow capability aspect, because if we have a fracture, basically it's providing additional surface area, material and energy exchange. And if the rock intrinsically has low porosity and as such they have low permeability, fracking the medium can increase the connectivity of these pore spaces, so that's why we are more likely to extract the materials in subsurface. And this kind of applications makes fractures particularly important in the context of hydrocarbon production, groundwater and chemical transport, as well as geothermal energy extraction. And in a lot of conditions, flow properties and elastic properties, although they may seem a bit of different, but then they actually coexist and they're implicitly linked together to each other. And think about simple picture of single fractures as a result of two rough surfaces in contact. So the open area here is going to give you open spaces which we call fracture apertures. So the volume of this open area and the connectivity of these areas is going to provide the flow capacity and also flow characteristics to the medium. And at the same time, the context in this medium is going to provide structural support to the fracture, and as such, together with this stress-free area of the fracture, they contribute to the elastic properties. So we can see from here that the implicit linkage is that the aperture distribution is going to give rise to both the flow properties and the elastic properties of fracture at the same time. And we can also see in another dimension, which is the stress dependency of this linkage, because when the fracture is subjected to a different stress level, then when it compresses or it releases, there will be distinctive changes in the relative proportion of open and closed area, and as such, this picture will and the connection will have another dimension of aperture and also stress dependency of these properties. So the idea is that if we know the linkage between flow properties and elastic properties well enough, then eventually we can have a way of inferring how the aperture distribution actually looks like for a particular fracture. So it all begins with a way to describe the medium of the fracture. So we have to think about intrinsically the rock surfaces are rough in nature. So no matter which scale we're looking at, for example, we can look into a visible light scale as a camera picture, and we can also look in the micron scale, which is a picture obtained by SEM, scanning electron microscopy. We can see the rock surfaces are rough in nature, and this roughness are random, but actually they're self-similar. So in this kind of scenario, we have to use statistical representation in order to describe a medium. So we are seeing two correlated rough surfaces in contact, and in a lot of situations, it's sufficient to consider a simplified picture, which the fracture aperture is a result of a flat surface and a rough surfaces. In this way, we don't have to come up with two descriptions with two surfaces, but instead we only have to provide one description for the first contact aperture, when we are only considering fractures under normal stress compression. And this kind of aperture distribution can be parameterized by two factors. One is the spatial autocorrelation length, which is given rise by the original correlation extent of these rough surfaces, and the other one is the relative surface roughness of these surfaces. So this one will control how much varying the small and the large aperture sizes are. And besides this, another very useful piece of information is that we know that from experimental observations, first contact fracture apertures actually follows log normal distribution. So this is another piece of information we can use to describe synthetic fracture aperture. So essentially, this is a picture we're looking at for our simulation. So we are considering a single fracture in cubic host rock, which is assumed to have the property of a granite. And we're looking into cubic rock of 100 meters in length scale, because we're mostly interested in the application of a large single fracture in the field environment. And steady state flow is undergoing across the fracture, and the fracture is under static compression. So we are going to perform numerical simulations on the stress dependency of the flow properties and elastic properties. So by flow properties, there are different ways of looking at it. For example, we can look into the permeability of the fluid flow. And on the other hand, we can also look into electricity flow by examining the electrical resistivity. And more transiently, which is a shorter length scale perspective, we can look into the characteristic and the statistic of particle transport across the fractured medium. And for elastic properties is more simple, because conventionally in field environment we depend on measurements of elastic wave velocities. So here we are representing the elastic properties with the primary wave velocity, and we are doing this considering different aperture distribution of this single fracture. We look into different properties and we try to draw linkage, and eventually we obtain insights for the corresponding inverse problem. And this is some examples of the symplectic apertures we can create using a method of fast Fourier transform. So if you compare across the top panel, this is the difference as a factor of lambda, which is the autocorrelation length of the fracture apertures. We can see that the longer autocorrelation length there are, the medium is more towards a homogeneous medium. So there are less spatial variability of aperture heights in here. And if you look into particular, overall histogram distribution of these aperture sizes, different lambda essentially is going to give rather similar distribution of overall aperture sizes. So the effect is more like redistributing different apertures of different heights across space. And if you compare across the lower panel, then it's the effect of sigma, which is the relative surface roughness. So larger relative surface roughness is going to give larger apertures. So as it is reflected in the histogram of having a heavy tail, because there's a larger variation and more high likeliness, we are seeing large apertures. And given the condition of same mean apertures, then in those with a higher sigma is going to have more contacts here. And this is what we can be seeing with same randomness distribution. So in order to examine for the fluid flow properties, and this is a way we can look into it by doing simple Darcys flow simulation. So doing this we can describe the steady state flow velocity as a result of constant boundary pressure applied to the medium. And assume the fracture is locally parallel, then the local permeability factor is going to relate to aperture height in a squared relation. And eventually, by evaluating the outgoing flux on the outer boundary, then we can have a way to infer for the effective permeability of a rock. And the story is similar for modeling the steady state electricity flow. So the direct current, electric current, is going to be as a result of the applied potential difference across the host rock. And what is a bit different compared to fluid flow is that the electricity flow can also happen in the contact region and also the rock body. So the conductivity of electricity is going to have a factor on the fluid conductance, which is happening on the open apertures, and the other perspective is on the rock body. So by evaluating the electrical resistance from the outlet, then and we can have way of telling the effective resistivity of a rock. So for the transport, we can also do a simulation with spatial Markov modeling. So this is some kind of model that can tell us if we inject uniformly along the high pressure boundary here and allow this fictitious particle to drift through the medium, so what is the amount of time each particle is going to take in order to complete its transport. So this kind of model actually simulates for two things. The first thing is the transportation pathway, in which the probability for each particle to go into different nodes is going to depend on the relative weighting of the outgoing velocities here. And the other thing the model is trying to calculate is the residence time for each particle at different particular location along its transportation path. So the amount of time each particle is going to spend at each location is going to depend on both the background flow velocity and also a factor of Brownian motion, because microscopically the particles could be bombarding against each other, and this factor can be modeled by exponential distribution with a standard deviation of the mean residence time. And this type of problem has a quasi-analytical solution in which the particle breakthrough distribution is going to drop almost linearly against time. So if we examine this slope here, then we can have a way to tell how heterogeneous the medium are, because it is the slowest transported particles that is actually drifting across the whole domain. So most importantly and finally, then the elastic wave velocity, we can borrow some concept from the crack model, because single fracture is actually also inducing vertical transverse isotropy, and we can have a Hudson-James model, which is original model built to evaluate this VTI medium as a result of ellipsoidal cracks. So there are certain adaptations here we need to make use of before we can apply in the context of single fracture. For example, we need to consider we need to have a way to translate aperture height into the aspect ratio of ellipsoidal cracks. And the other thing is that we should be considering weak inclusion formulation, because actually in the fracture, if we apply a pressure perturbation, actually fluid can drain out of the medium. So the model actually has a few components, which is depicting the moduli of isotropic rock and also first and second order correction as a result of the cracks. And the effective moduli is evaluated as the combination of these components using a per-day approximation. And in particular, the effective moduli C33 star, we can use it to evaluate the vertical traveling primary wave velocity, and by looking at the ratio between it and also the average density, and take a square root of it. So this is how we are going to do our simulations. And we are considering 49 sets of different roughness parameter here, and in particular 7 different lambda level between 1/16 of a length scale to a 1/16 of a length scale. And just to remind you, we are looking in the large single fracture, and L here is representing 100 meter. And also at the same time 7 different sigma between this and this interval. So we can look into the joint flow properties as reflected by the permeability velocity, resistivity velocity, and also transport velocity relations. So this is how they look like under different effective stress for different roughness parameters. So we can examine the power of these relations on characterizing what the medium actually looks like by by separating in the discussions into the property of each of them for different lambda and different sigma. So first of all, let's take a look at the probability VP relation. So on your left is same lambda, different sigma, and on your right is different lambda, same sigma. So from the distinctiveness of these lines, we can tell that the probability VP relation is going to be differentiable for both lambda and sigma across all the stress range. And in particular, it's more apparent when we are seeing under a high effective stress level. And this is because probability is a collective effect of both parameters, while the velocity is mostly dependent on relative roughness only. And in particular, under a high effective stress level, then the medium becomes more restrictive on flow. Then the distinctiveness between different inhomogeneity becomes more apparent. For resistivity VP relation, we are also seeing it as differentiable for the factor of relative roughness of all stress range. However, it is shown to be not too helpful for differentiating the different spatial correlations, because the conductivity of electricity does not only depend on the open area, it can also happen in the bulk rock volume. So the information of lambda is a bit masked out here. So there will be insufficient resolution to differentiate with this factor. And most importantly, the transport VP relation, which I think is most interesting because first of all, it is shown to be very distinctive for lambda across all stress range. And a bit different from probability is that we are seeing that this transport VP relation is differentiable for lambda, but not under a high effective pressure stress condition. It is more usable under the low effective stress region. It is because the particle transportation is more sensitive to individual geometry, and as the flow is more conductive, then we are having higher likeliness to see the variation between the transport time. But when the fracture is more closed down, then the development of anomalous transport is going to make transportation time increase exponential in time. So this is why when the flow is very restrictive, the transport is not going to tell us too much information. So conclusion here is that what we have done is that we are looking into fracture joint properties and establish from the respective stress dependency of fracture properties by looking into different aperture distribution, and we are approaching this problem by numerical simulation. And we have looked into the characterization power of apertures from different joint flow elastic properties. For instance, we have seen that probability velocity relation can be used to classify both the spatial and global heterogeneity of these aperture volumes, and as well as the transport velocity relation. And the difference is that transport velocity relation is going to be applicable under a low effective stress regime, which is actually supplying another piece of information than these conventional relations we have been looking on. So the key message here is that I try looking into more transport properties of the medium, because they are shown to be a very informative alternative indicator for characterization purpose. So these understandings of characterizing the fracture medium from flow elastic properties has certain real-world implications. For instance, we're keen to classify and look into examine the risk associated with active earthquake-inducing faults. So right now we have scientific drilling method to acquire near-field data in order to characterize the fault structure. So I hope this study will provide certain insights on how much characterization power we can have for different kinds of measurements and what kind of measurements we're making. And on industrial perspective, nowadays we often rely on hydraulic fracturing in order to produce hydrocarbons from unconventional reservoirs, which compose of very low porosity shale rock. And this is going to help us to identify how much these created hydraulic fractures are actually looking like geometrically, and help us to predict certain measures, what is the correct measures we can be employing in order to enhance the productions in these artificial fractures. So thank you very much, and Finally, we can summarize what I've discussed in this simple track. So we've looked into the stress dependency of different properties of fracture, and by looking at the sensitivity of the joint flow elastic properties, then we can have the discussion of inferring of how the aperture distribution actually looks like. And I encourage you to take a look at our website in order to keep track of the progress of this research and other area of geophysics research we have been working on, and all of these written documents and also research papers could be found on our website as well. So thank you very much. And again, so we are from Singapore Geophysics Project, National University of Singapore. So stay tuned for our next presentation. Thank you.